So, today we will continue our discussion on the relativistic quantum mechanics. How do we describe particles and their interactions in that? So, in the case of non-relativistic quantum mechanics, we had the Schrodinger equation minus h cross square over 2m grad square psi plus V, the potential interacting potential psi equal to I h cross dou by dou t, the energy operator acting on the wave function psi. And as we said, this is not adequate to describe the relativistic dynamics. So, for the relativistic case, we had discussed what is called the Klein-Gordon equation. This is basically based on the energy momentum relation E square is equal to P square plus m square, where we are now working in units of h cross is equal to 1 is also equal to c. In that case, we said we could write down for a wave function particle described by a wave function phi dou mu phi plus m square phi plus v phi equal to 0, where dou mu is now dou by dou t, and we discussed discussed the interaction of charged particles, and to some extent found out the expression for transition amplitude in this case. Another approach to get to the relativistic equations is due to Dirac, and we will see that we can get some other dynamical equation describing the wave function's evolution, which is known now as Dirac equation. In the case of Klein-Gordon equation, we used E square is equal to P square plus m square. In the case of Dirac equation, what we will do is to linearize this thing. Remember, the problem in Schrodinger equation was that it is quadratic in the coordinates, in the position coordinates, and or the second order derivative in the position coordinates, but first order derivative of time parameter. So, and then in Klein-Gordon equation, we took both of them to second order, and in Dirac equation we go the other way and then try to get the first order kind of this. So, it is now written as some coefficient alpha dot p. Alpha is given a symbol of a vector and dotted with p. The meaning is essentially that alpha 1 some coefficient multiplying the first coordinate of momentum, another coefficient alpha 2 p 2 plus alpha 3 p 3 plus beta m psi. This is actual meaning of this, but in a compact way we can write it as alpha vector dot p. Whether alpha is actually a vector or not, we will see later. Now, what are these alphas and betas? For that we will actually again rely on the energy momentum relation. We know that h square psi should be p square plus m square psi. since energy operator, the Hamiltonian operator, square of that when it acts on psi, it will give you the square of energy as the value if psi is the eigen state of energy, and then usually we take psi as the eigenstate of energy, which is a physical state. So, E square is equal to P square plus M square is what we have. But from 1, if you take h square and if you take the square of the operator on the right hand side, you will have alpha 1 dot P 1 dot P 1 plus alpha 2 dot not dot, actually just ordinary multiplication, alpha 3 P 3 plus beta m square psi. That will give you let me call this equation, the energy equation, as 2. S square psi then is equal to, so I have alpha 1 square P 1 square plus alpha 2 square P 2 square plus alpha 3 square P 3 square plus beta square m square psi plus other terms alpha 1 alpha 2 P 1 P 2 plus alpha 1 alpha 3 P 1 P 3 plus alpha 1 beta m P 1 acting on psi plus similarly alpha 2 alpha 1 P 2 P 1 plus alpha 2 alpha 3 P 2 P 3 plus alpha 2 beta m P 3 acting on psi, alpha 3 alpha 1 P 1, actually P 3 does not matter here, P 3 P 1 alpha 3 alpha 2 P 3 P 2 plus alpha 3 beta m P 3 psi. The earlier one is actually P 2. Then one more term beta alpha 1 P m P 1 beta alpha 2 m P 2 plus beta alpha 3 m P 3. So, these are the terms when you expand it. I have deliberately expanded it in explicit fashion, so that we will not confuse ourselves. And we also did not assume that alpha 1 alpha 2 is equal to alpha 2 alpha 1. P 1 and P 2 are momentum operators which we know commute. P 1 and m also commute. Similarly, other components of P 1 P also commute with each other and also commute with other commute with mass m. But the other coefficients alphas and beta we are not assuming to be commuting, and we will see what are the relations that it should follow. Say for example, if you take it to be commuting, what happens? If you take they are commuting, then it will be a problem. So, let us look at it. H square psi equal to alpha 1 square P 1 square plus alpha 2 square P 2 square plus alpha 3 square P 3 square plus beta square m square psi plus P1 and P2 and P2 and P2 P1 and P2 P1 P2 are the same, they commute. So, I combine alpha 1 alpha 2 plus alpha 2 alpha 1 P1 P2 acting on psi plus alpha 1 alpha 3 alpha 1 P1 P3 psi alpha 1 alpha yes alpha 1 beta plus beta alpha 1 MP1 psi plus alpha 2 alpha 3 plus alpha 3 alpha 2 m P2 P3 psi plus alpha 2 beta plus beta alpha 2 MP2 psi plus alpha 3 beta plus beta alpha 3 MP3 acting on psi. These are the only terms. Now, let us look at the relation, energy momentum relation, that let me write it here again, equation 2 that we had written earlier. H square psi is equal to P square plus M square psi. That is equal to P1 square plus P2 square plus P3 square plus M square psi. But now, the first line here in H square psi, what we have is alpha 1 square P1 square plus alpha 2 square P2 square plus alpha 3 square P3 square plus beta square M square psi. And there is no other term with P1 square, P2 square, P3 square or M square. So, the coefficients of P1 square, P2 square, P3 square and M square should all be equal to 1. That is one condition. Let us put that there. So, alpha 1 square equal to alpha 2 square, alpha 3 square equal to beta square equal to 1. All of them are the same and equal to 1. Then other thing is alpha 1 alpha 2 plus alpha 2 alpha 1. Suppose we put, and there is no such term in the H square, because H square is P square plus M square and that is already accommodated. Now, the rest of it, all the terms should either cancel with each other or should vanish identically. So, the first term is proportional to P1 P2, second term is proportional to P1 P3, then MP1 P2 P3 MP2 MP3. Either some of these components are zeros, if P1 is equal to 0, P2 equal to 0, P3 equal to 0, M equal to 0, then everything is fine, but that anyway will give you null result H square is equal to 0. So, that cannot be, but then the other thing that can happen is coefficients of P1 P2 identically goes to 0. It should be valid for a general momentum, any momentum it should be valid. Okay. It does not matter what a particular case P1 or P2 equal to 0, one particular term will vanish. But in general, if you want this to be so, then each of these coefficients alpha 1 alpha 2 plus alpha 2 alpha 1 should vanish, and they will vanish like that only if either alpha 1 alpha 2 r or either of this is equal to 0, that will also not give you a general case, because otherwise there won't be either a p 1 square or a p 2 square term there in H square, which is not allowed, which is not a general case. So, now alpha 1 alpha 2 plus alpha 2 alpha 1 is equal to 0 means they are objects which do not commute. So, these are no ordinary numbers or ordinary functions. So, that tells us that alpha I alpha j plus alpha j alpha I equal to 0 if I is not equal to j. I equal to 1, j equal to 2, it is alpha 1 alpha 2 alpha plus alpha 2 alpha 1, which is equal to 0. And similarly, you have alpha I beta plus beta alpha I equal to 0 for all I equal to 1, 2, 3. These objects therefore are called anticommuting objects. Because if you switch the order in which they are multiplied, that will give you a change of sign. So, that is one thing. Now, okay, so that is one thing that we notice. Now, let us say we said alpha 1 square equal to 1. It is not an ordinary function. We know, we are familiar with one type of this anticommuting objects. Matrices in general do not commute. If you take a matrix A and a matrix B, multiply it together, so that you have first element A and then B, matrices A or M 1 and M 2 in general is not equal to M 2 M 1. That is clear to you, because you are familiar with these matrices. So, it could be a matrix. One of the ways this can be represented is through matrix, and we will certainly be doing that. So, at least some mathematical entity we know which actually are not which can be non-commuting. Now, if you have a matrix form say, and then suppose you have diagonalized this matrix. If you diagonalize this matrix, then you have only diagonal elements for this lambda 1, lambda 2, etc. Then alpha 1 square is essentially lambda 1 square, lambda 2 square, lambda 3 square, etc. So, the other elements are all zeros, only the diagonal elements exist. Okay. Depends on how many, what is the dimension of the alpha. So, when I write it as lambda square equal to 1, I actually mean a unit matrix. So, this is a unit matrix, and a unit matrix is a diagonal matrix with diagonal entries equal to 1, etc. Which means that lambda 1 square is equal to lambda 2 square equal to lambda 3 square equal to 1, etc. Okay. So, etc. All of this diagonal elements should be equal to 1. This 1 is actually just 1, the number 1, not any matrix. And that then tells you that the eigenvalues lambda 1, lambda 2, lambda 3, etc. of alpha 1 is either plus 1 or minus 1. So, the lambda eigenvalues can be either plus 1 or minus 1, nothing else. So, it cannot be 0, it cannot be plus 1, it cannot be minus 1 or any other number, it can be either plus or minus 1. That is one consequence. Then let us look at the property of the anti-commuting property of alpha I. Let us specifically take alpha 1 and then, or I can write as alpha beta is equal to minus beta alpha 1. Now, let me multiply this by beta from the left side. So, that will give you beta square alpha 1, but beta square is equal to 1, therefore, it is equal to alpha 1. Let me now take the trace of this beta alpha 1 beta trace of or minus the trace of alpha 1. But now, we have a property of the matrices, trace of a chain of products of matrices say A, B, C is equal to, it is unchanged if you cyclically rotate this C, A, B. That is an exercise which you can prove later on. That will tell you that trace of beta alpha 1 beta is also equal to trace of beta square alpha 1, that is equal to beta square is equal to 1. So, that will give me trace of alpha 1 is equal to minus trace of alpha 1. This is possible only if trace of alpha 1 is equal to 0. A quantity is negative of the same quantity only if that is identically equal to 0. So, there are two such properties that we found. Similarly, for other alpha values and even for beta. So, we can replace alpha 1 by alpha 2 or alpha 3. So, that will immediately tell you alpha 2 trace is also equal to 0, and instead of multiplying the second line here by beta, if I multiply by alpha 1, then again I will get alpha 1 square equal to 1 will give me trace of beta is equal to 0. So, trace of all of this is equal to 0. Now, what does that tell us? 1 is eigenvalue either plus 1 or minus 1. Trace. So, let us say, let us take an example. If I take 2 by 2 case dimensional matrix, then say alpha 1 can be in the diagonal form 1, say minus 1. Just an example. So, let me take alpha 1. This is now traceless, eigenvalue is either 1 or plus 1 minus 1. But now, let me take a 3 by 3 case. So, let me take alpha 1. One possibility is to take 1 1 1, because then that is a unit matrix. So, obviously, the trace of that is not equal to 1, but can I make one of them minus 1, the other is plus 1, and then also trace is minus 1 plus 1. This is not possible to have a traceless. You cannot have eigenvalues either plus or minus 1 and at the same time trace is equal to 0 for an odd dimensional case. That actually tells you that, in fact, these two tells you that it is an even dimensional matrix. Now, alpha, the other property of alpha I and beta is that they are Hermitian. And how do we see that? H psi is equal to alpha 1 p 1 plus alpha 2 p 2 plus alpha 3 p 3 plus m beta psi. Since H is Hermitian, P is Hermitian, and M is anyway constant Hermitian, that will tell you that alpha I is Hermitian and beta is Hermitian. So, this is another property. So, alphas and betas are Hermitian objects. Dimensionality is, it should be an even dimension. I think either 2 by 2, 4 by 4, 8 by 8, 6 by 6 or whatever. Cannot be odd dimension, 3 by 3 is not possible. Eigenvalues are either plus 1 or minus 1 and they are traceless. Let us take 2 by 2 case, lowest even dimension, 2 by 2. Let us take a general matrix A, B, C, D. Hermitian will tell you that A, B, C, D, A dagger is equal to A, B, C, D itself, and that will tell you that. Okay, so, the Hermitian thing is left hand side is A star B star, first the conjugate transpose. So, LHS is equal to A star C star B star D star. So, that should be equal to RHS, tells you that A is a real number, B is equal to C star and D is equal to D star, the real number. So, the diagonal elements are real, off diagonal elements are complex conjugates of each other symmetrically. That is what will happen if you have larger dimensions. So, let us take 2 by 2 and then this is how it is. So, any Hermitian matrix you can write as A, B, B star, D, fine. So, now let me see if I can write it in terms of 0 1 1 0 plus 0 minus I 0 plus 1 0 0 minus 1 plus some C 0, for whatever reasons I am denoting it by 0. So, the last one here is a unit matrix 2 by 2 and you recognize the first 3 as the Pauli matrices. If I do this, first element only C 3 and C 0. Okay. So, let me write it in that order, C 0 and C 3, C 0 plus C 3, the second C 1 minus I C 2, C 1 plus I C 2 and C 0 minus C 3. Indeed, the off diagonal elements are complex conjugates of each other, diagonal elements are real. Now, provided the C's are diagonal, C's are real numbers. What does this mean? Otherwise, this is arbitrary. C 1 can be any number, C 2 can be any number, C 0 can be any number, C 3 can be any number, which says that a 2 by 2 general 2 by 2 Hermitian matrix can be written as a combination of these 4 matrices. They are called the Pauli matrices. Pauli matrices, sigma 1 is 0 1 1 0 of diagonal, sigma 2 is 0 minus I 0 of diagonal, sigma 3 is diagonal 1 minus 1. So, the Pauli matrices along with the unit 2 by 2 unit matrix is enough to describe any arbitrary Hermitian matrix of dimension 2 by 2. And you can also see that sigma 1, sigma 2, sigma 3 do not depend on each other, or they are linearly independent of each other. You cannot get one in terms of another one. By observation you can see that. Also, I mean just multiply one by some number, you will not get the other one. Okay. Then the unit matrix is also linearly independent of this. So, we have 4 linearly independent matrices in terms of which we can write any other matrix. This means that if we have to consider alpha 1, alpha 2, alpha 3 and beta, the Dirac matrices, in 2 by 2 matrix form, it is enough to actually consider sigma 1, sigma 2, sigma 3 and beta and the unit matrix, because any other matrix you consider can be written in terms of this anyway. And now, if you look at the anti-commuting properties, and alpha I, alpha j plus alpha j, alpha I equal to 0 for I not equal to j. All of them anti-commute with all the others, but in the set we have along with the Pauli matrices, we have a unit matrix and that commutes with everything. So, we cannot have 4 linearly independent matrices which anti-commute with each other in case of 2 by 2 matrices. So, 2 by 2 is not enough. So, the next thing to consider is the 4 by 4. 3 by 3 is an odd dimension. So, we will not be able to look at that. Now, looking at the 4 by 4 matrices, let us look at that is the minimum dimension for Dirac matrices. There is one particular representation called Dirac Pauli representation. This is alpha 1 is 0 0, 0 1 1 0, 0 1 1 0, 0 0 0 0, alpha 2 0 0 0 minus I 0, alpha 3 equal to 0 0 1 0, 0 minus 1, 1 0 0 0 0 minus 1 0 0, and beta equal to 1 0 0 1 0 0 0 0 0 minus 1 minus 1. right. This particular representation, I would like you to check that they satisfy all the anti-commutation relation and also that their square is equal to unit matrix. In a compact way, you can write alpha as 0 sigma sigma 0. Sigma is a Pauli matrix, where now you have to, when you consider alpha 1, sigma 1 is considered, alpha 2, sigma 2, alpha 3, sigma 3, and beta is a unit matrix and minus of the unit matrix. Each of these entries here are 2 by 2 matrices. So, it is written in block form. Okay? And you can check this. This is only one representation and there are other possible representations too. Which will give the same physics. So, there is no unique representation. It can be this Dirac Pauli representation. It could be some other also. We might mention some other representation which is interesting in particle physics. Okay. So, now let us consider the Dirac equation again. H psi is equal to alpha dot p psi plus beta m psi, where now alphas and beta are 4 by 4 matrices, and therefore, psi should be a 1 by or 4 by 1 matrix. So, H I will have actually psi 1, psi 2, psi 3, psi 4, a 4 component object. Alpha is a 4 by 4 matrix dotted with P, and then you have a, so alpha dot P itself is a then a 4 by 4 matrix. Then you have psi 1, psi 2, psi 3, psi 4, a 4 by 1 matrix, so that they can be multiplied, plus similarly beta m is a 4 by 4 matrix, and you have psi 4 by 1 matrix. This should be kept in mind. Let me but now take this first equation here 1 and multiply by, or first let me take the so let me take this equation, the Dirac equation, and write it in the operator form. I dou by dou t, the Hermitian the Hamiltonian energy operator acting on psi is equal to alpha dot minus I gradient, which is the momentum operator acting on psi, plus beta m psi. Multiply this by beta from the left will give me I beta dou by dou t of psi minus I beta alpha dot grad psi plus beta square m psi, beta square is equal to 1. Now, I can bring this to the one side. So, I will have I beta dou by dou t plus I beta alpha dot del acting on psi minus m psi equal to 0, beta square is equal to 1. let me introduce a notation gamma mu equal to beta and beta alpha. So, gamma 0 is beta, gamma 1 is beta alpha 1, gamma 2 is beta alpha 2, gamma 3 is beta alpha 3. In this notation, now I can write the Dirac equation as I gamma 0 dou by dou t minus I gamma I dou I and psi minus m psi equal to 0. Here dou mu is equal to dou by dou t and grad minus sorry, this is plus. Okay. So, dou mu, so this will be then plus that way. So, together I can write it as gamma mu dou mu minus m psi equal to 0. Just to remind you that it is a matrix equation. We will write this matrix indices explicitly. A b element of I gamma mu multiply dou mu psi element b element of this dou mu psi and subtract, so that will give you a element of gamma mu dou mu psi and subtract by m psi a will give you 0, where a and b are Dirac indices 1, 2, 3, 4. So, this a and b runs through the Dirac components, the components of gammas and components of psi. So, this is not, this has nothing to do with the Lorentz index mu or the components of vector in that sense. So, this is what we have here for this, and now let me look at the properties of alpha and beta written in terms of gamma now. Beta alpha I plus alpha I beta equal to 0. Let me multiply it by beta. Beta alpha plus beta alpha is equal to beta alpha I beta equal to 0. So, that is beta is gamma 0, beta alpha I is gamma I plus gamma I beta alpha I. Let me club them together in this fashion, gamma I gamma 0 equal to 0. So, this is one thing. So, gamma 0 and gamma I for any I commute, anti-commute. Take alpha I and alpha j for alpha not equal to j, sorry, I not equal to j, commute, anti-commute. Multiply again by beta alpha I, alpha j, beta from both sides. Okay. Alpha j, alpha I, beta equal to 0. When you, because of the first line here, beta alpha is equal to minus alpha I beta, I switch these beta and alpha j in the first term and beta and alpha I in the second term. That will give you a minus sign in both cases. So, I should have added a minus sign here and then put this as a minus sign equal to 0, but because of an overall that will give you only an overall minus sign. and the first one is gamma I gamma j plus gamma j gamma I equal to 0. Okay. So, now that is so we have two relations here. One is let me highlight those. One is this, that is gamma 0 gamma I plus gamma I gamma 0 is equal to 0, and we have another relation gamma I gamma j plus gamma j gamma I for I not equal to j equal to 0. So, gammas anticommute as well. Okay. So, this is the same as the relation that we had in the earlier this in case. And now, some other properties of gammas. Alpha I square equal to unity, okay, which will give you, let me write it as beta alpha I beta equal to beta square. I just multiplied by beta from both sides, and then again that will give me I have to, the first one is beta alpha I, second one I switch this beta and alpha. So, I have beta alpha I with a minus sign is equal to 1, which is basically gamma I or gamma I square equal to minus 1 because of the minus sign here, and beta square is obviously equal to 1. So, gamma 0 square is equal to 1. So, beta square gamma square is equal to 1, gamma 0 square is equal to plus 1, and gamma I square is equal to 1. Putting together all these, the anticommutation relation, these two relations, and this property of the square of the gammas, we can write gamma mu gamma nu plus gamma nu gamma mu equal to 2 g mu nu. I would like you to verify that these in components are exactly the same as what we have now written here. Okay. So, that is essentially the thing that we want to discuss. There is one exercise that I would like you to have. So, what I will write the exercise here, you just show that gamma 0 dagger is equal to gamma 0, which is obvious because it is beta itself, but more importantly gamma I dagger is equal to minus gamma I. One thing that I had not mentioned, but is somewhat obvious the way we had written, is that gamma I runs from 1 to 3, whereas the Greek indices run from 0, 1, 2, 3, 4 dimensions. So, this is another property, the hermiticity. So, I will leave it as an exercise for you. Please check that. Okay, so we will consider other aspects of this Dirac equation in the coming lectures.